Hello. In the last two movie segments, we developed the story of the atom. And we stopped the second segment by describing Bohr model of the atom, which beautifully explained the various energy levels, and it explained the discrete spectrum, the different colors of the hydrogen spectrum. So, do we have a perfect picture of the atom? Well, the answer is no. It is far from being perfect. Why? Because Bohr model of the atom only explains the simplest of the spectrum of hydrogen. Hydrogen is a very simple element, one proton and one neutron, and the possible electronic transitions are limited, and it explains the beautiful red, yellow, green, blue, violet, and so on. But now if you go and look at the spectrum of higher elements like helium, lithium, and higher, the spectrum gets more and more complicated. The Bohr model does not really explain this complicated picture of the atom. So we need to now modify our theory, and that is where the quantum theory of the atom comes in. What you see here is helium light. I'm going to allow the light produced by a helium source to pass through a diffraction grating, and I want you to look at the spectrum. Look at the profusion of lines in the spectrum. There are a lot more lines in the spectrum of helium than in the spectrum of hydrogen. So in order to explain a complex spectrum like this, Bohr model of the atom is not sufficient. We've got to look for something else. So that is where we begin to discuss the quantum mechanical model. The basis of quantum theory is a theory introduced by Louis de Broglie in 1921, in which he said, all matter behave like waves as well. In other words, the duality of matter. Now, that is an important concept, where you and me, electrons, mountains, little balls, they all have wave nature and particle nature. Now, what are the characteristics of a particle? A particle, of course, has mass, and it can move with a certain velocity, which means it has momentum. What are the characteristics of waves? When you hear about a wave, you've got to ask, what is waving? When we talked about a wave, we talked about the variation of amplitude. What is waving is the variation of the amplitude. So, a particle can behave like a wave? Well, let's see how the theory was evolved from this duality of. Now, de Broglie suggested that particles could sometimes behave as waves, and waves could be interpreted as particles. Now, one such particle that we discussed so far is the particle called photon. You remember in Bohr model of the atom, when an electron jumps from one energy level, a higher energy level, to a lower energy level, it emits a packet of energy. And we said that packet of energy is h times the frequency. That is a quantum of energy. And that can behave like a particle. And the particle has wave characteristics. Well, we can actually develop a model of the atom based on that. Now, a particle has a momentum p and wave has a wavelength lambda. That means if you have to assign a duality, a dual nature, then you have to find a relation between these two. Is there a relation between momentum of a particle and its wavelength? Indeed, there is a relation between momentum and the wavelength. And this is the equation that de Broglie came up with. Lambda equal to h over p, Look at where that H comes from again. What does H stands for? It is the Planck's constant, and its approximate value is 6.64 times 10 to the negative 34 meter squared kilogram per second. And since momentum equal to m times v, we can write lambda equal to h over mv, a very important relation. Well, does it mean that you can measure my wavelength, your wavelength, the wavelength of this stick? Well, let's have a look. A small problem. What is the de Broglie wavelength of a ball of mass 0.15 kilogram thrown with a velocity of 40 meter per second? That'll be interesting. It's a very simple problem, is that right? Lambda equal to h over mv, p equal to mv. So h we know, m and v are given, and look at that wavelength. It is 1.1 times 10 to the negative 34 meter. How big a wavelength is that? Well, if you measure my wavelength, it will be much shorter because my mass is greater than the mass of that ball. Is that right, when I move with a certain velocity? Well, because it is so small, it is very difficult for us to discern it. And therefore, associating a wave with a particle, for us it is not very practicable, we would say. But it becomes very clear when the particle becomes very small. And let's see in the next problem, what is the de Broglie wavelength of the wave associated with an electron that has been accelerated from rest through a potential of 50 volts? Well, I have not given you the velocity of the electron. Is it possible to find the velocity from here? Well, you know that energy, well, in the last lesson I told you about electron volt. What is an electron volt? Small energies are measured in electron volts. If an electron is subjected to a potential difference of 1 volt, the energy, the kinetic energy acquired by that is 1 electron volt. And that 1 electron volt is equivalent to the charge on an electron. It is 1.6 times 10 to the negative 19 joules. That means if you subject an electron to a charge of 50 volts, the energy it will acquire will be the charge of the electron multiplied by the voltage. Is that clear? Well, 1 electron volt is 1.602 times 10 to the negative 19 joules. And this is the energy of 1 electron, 1e, when subjected to 1 volt. Now, that is E electron volts. When 1 electron is subjected to a potential difference of 1 volt, the energy it acquires is E electron volt. Therefore, if an electron is subjected to V volts, a potential difference of V volts, the kinetic energy it will acquire will be E times V joules. And we can take that E times V joules and equate it to 1/2 mv squared and calculate the velocity of the electron from this given data. That's what we're going to do. Alright, let's do that now. So the work done in accelerating an electron by a voltage V is E times V. Work done is a measure of the energy acquired by the electron. Now this becomes the kinetic energy of the electron such that 1/2 mv squared equal to E times V, and we can solve for the velocity of the electron from there. That will be V equal to 2eV divided by m. We know all these values. The charge on the electron, the potential difference is given, the mass of the electron we know, is that right? And using all those values, we get the velocity of the electron is 4.119 times 10 to the 6 meter per second. Now, we know the velocity, we know the mass of the electron. and therefore we can now calculate its de Broglie wavelength. What's the equation for de Broglie wavelength? Lambda equal to h over mv, and using all the known values, it gives me 1.74 times 10 to the negative 10 meter, which is 0.174 nanometer. Well, is that a small number? Well, in our daily life, that is a very small number. But it is really not a small number when the size of the electron is taken into consideration. You see, if you want to compare that wavelength, which is 0.174 nanometer, with the diameter of an electron, actually 0.174 nanometer is hundreds of times the diameter of an electron. That means when compared with the size of the electron, this wavelength is very considerable. That means an electron has considerable wave characteristic. It can be a particle, at the same time it behaves like a wave. So the dual nature becomes very obvious when you go down to the very level of minute particles. Well, let's now talk about Schrödinger wave equation. Now, you've got to appreciate one thing. We are taking a big concept of quantum mechanics. There are volumes of books written on it, and I'm going to condense that idea into one of these classes, about roughly 1 hour. So I will simply pick ideas and try to develop the model of the atom from there. Now, Schrödinger wave equation. What is a wave equation? We discussed the wave equations before. For a vibration of the particle, the wave equation tells you where the particle is at a given time. Is that right? In fact, you know that we obtained equations like y as a function of x and t, position and time, equal to a sine kx minus omega t. Do you recognize that equation? Well, that explains the waving part of a particle. Now, can we develop such an equation to describe the electron? And Schrödinger equation is such an equation. Schrödinger's equation gave a much more precise description of the electron's location and energy than Bohr's model. Well, remember, Bohr's model did not give you a clear idea beyond the hydrogen atom. It is the Schrödinger equation came in and described it in much more detail using the quantum model. Now, the wave function for a classical wave traveling with a wavelength lambda and amplitude a, the classical wave is the wave that we have discussed earlier, is this. Psi xt, in place of y, the displacement, I use the letter psi. In fact, that is Schrödinger's notation. Is a sine 2 pi x over lambda minus omega t. Now, this is the same. 2 pi divided by lambda is the wave number k. So a sine kx minus omega t, that is the normal description of a wave we discussed earlier. Now, it is reasonable to assume that this wave function is associated with the particle's energy, which is both kinetic and potential. So this wave function is actually determined by the energy of the particle. The particle, like an electron, has a potential energy because of its position, isn't it? Its potential energy is greater as it's farther away from the nucleus. It has kinetic energy because it has velocity. So this wave function really depends on its potential and kinetic energies. And Schrödinger proposed an equation for the de Broglie matter waves. So the de Broglie matter wave is actually made into more quantized form by Schrödinger equation. And he gave a picture of that wave by the wave function psi. Psi is the wave function which is used in this equation. Now, what is that wave function psi? Very often it remains an enigma for many quantum mechanics students, leave alone students like you who have no idea of quantum mechanics. Now, Schrodinger equation can be written like this. Psi, which is a function of the kinetic and potential energies, equal to E psi. E stands for the total energy. So what it tells you is that the wave function that describes the electron is actually a function of the total energy of the electron. And that can be used to locate. Can we locate precisely where the electron is? That's a different task. Well, if psi represents an electron beam, if we consider an electron beam, then psi squared is proportional to the number of electrons that can be found in a given volume. Now you notice that we used psi squared. When you square a quantity, a lot of ambiguity can be reduced because all the negative parts will become positive. That's why we square that psi. Now if there is only one electron, then what does psi square represent? Psi square represents the probability of finding the electron at a particular point. That's a positive quantity. So, as far as we are concerned, Schrodinger equation gives you a method of finding the probability of locating an electron at a particular point. Now, you must understand that Bohr's picture of the atom gave you the exact location of the electron, isn't it? We calculated the radius of a Bohr orbit. We know precisely where an electron can be found. But in quantum mechanical model, we cannot precisely determine where the electron can be found. But we can talk about the probability of finding the electron at a point. And psi squared, which is given by Schrodinger's wave equation, gives you that measure of probability. It is proportional to the probability of finding a particle in space and time. So psi is a function of space and time. Now, that leads us to another important concept in quantum mechanics. You can see I'm picking ideas, putting it all together, which is the Heisenberg uncertainty principle. I'm sure most of you have heard about it. Now, what does the uncertainty mean? Well, do I know exactly if this stick is in front of me? Is there any measure of uncertainty about its position? Well, as far as we are concerned, we would say, no, I know exactly where it is. But when it comes to a particle like an electron, which behaves both like a particle and a wave, it is very difficult to assign a specific position and determine where exactly the particle is. And it is therefore very important to discuss the uncertainty principle. In 1927, German physicist Werner Heisenberg developed what is now known as the Heisenberg uncertainty principle. Now, this hypothesis states that the position and momentum of an electron or any moving particle cannot both be known precisely at the same time. In other words, if I try to measure exactly where the electron is, I lose information about its velocity. If I try to measure precisely the velocity of a moving electron, I lose information about its position. That is what it means. Now, how can that be? Well, remember, electron is such a very minute, tiny particle. If you want to locate a particle, now, how do you locate me? Well, if I turn off this projector, you can see it is the light of the projector that makes you see me. If I turn off this projector now, you will not be able to see me. Look at this. Well, So if I have to locate an electron, I have to project a beam of light onto it. But light consists of these energy packets called photons, isn't it? And when these energy packets fall on the electron, they disturb its position. So the very fact that we use a beam of light to illuminate an electron so that we can look at it will change the position of the electron. So when you try to locate it, its position changes. So when you want to measure its location, its velocity changes. When you want to measure its velocity precisely, its location changes. Now this is where the uncertainty principle is important. We're going to represent delta x to represent the uncertainty in determining the position, and delta p in determining the uncertainty of momentum. That means if I can determine the position precisely, then the uncertainty in the momentum will be very large. If I can determine delta p precisely, then uncertainty in the position will be very large. And Heisenberg expressed this as an equation like this. Delta p times delta x is greater than or equal to h over 2 pi. Now that means the minimum value of this, the minimum value of delta p over delta p times delta x equal to h over 2 pi. So if I ask you to find the minimum uncertainty, I can change this inequality to an equation. All right. Now this can also be written in terms of the energy and time like this. Delta E times delta T is greater than or equal to h over 2 pi. Well, we will be using mostly this form of the uncertainty principle. Well, let's do a problem and see how that looks like. The speeds of an electron and a 20-gram bullet are both measured to be 300 meters per second at an instant. If the uncertainty in this measurement is plus or minus 0.010%, what is the minimum uncertainty in the position of each? What is the minimum uncertainty? Now, since we are looking for the minimum uncertainty, we can replace that inequality sign by an equal sign. That will be the minimum value. Well, what are the given data? The mass of the bullet is given, mass of the electron you know, the velocity of the bullet and the electron both are given. Now, the uncertainty in measuring the velocity is given. I want you to interpret correctly. It is 0.01%, means it is 0.01% of 300. So your delta V will be 0.01%. When you convert that to be a number, it will be 0.01 divided by 100, which is 0.0001 of 300. So we say delta V is plus or minus 0.0001 times 300, and that will be plus or minus 0.03 meter per second. That is the uncertainty in measuring the velocity. Now, it means the uncertainty can be anywhere from negative 0.03 to positive 0.03. So the actual spread is 0.06, and therefore we must use delta V as 0.06. That is the actual uncertainty. So the actual uncertainty is double this value, because you can have 0.01% above or below the actual value. Therefore, in our calculation, we got to use delta V equal to 0.06 meter per second. Now, for maximum uncertainty, no. You try to change this to minimum. Is that right? That's what we want to find. To find the minimum uncertainty for the bullet. We need to find the minimum uncertainty for the bullet as well as the electron. So if you change that maximum to a minimum, what will our equation be? It will be delta x equal to h over 2 pi delta p, because delta x times delta p equal to h over 2 pi. And therefore the minimum uncertainty in locating the bullet will be h over 2 pi times delta p, and delta p is the change in momentum, uncertainty in the momentum, which is mass times delta v. So we replace that. That will be h over 2 pi times mass of the bullet times delta v. I hope you understood this statement. We are looking for the minimum uncertainty in the position. Now, when the uncertainty is minimum, delta x multiplied by delta p equal to h over 2 pi. Alright, what all we now need to do is replace these values. We know the mass of the bullet, we know delta v, we just calculated, and h we know, and that gives you the uncertainty in measuring the position of the bullet is 8.8 times 10 to the negative 32 meter. You can see this is a very small value. So we can say for all practical purposes there is no uncertainty in measuring the position of the bullet. Because the bullet is a big object, the uncertainty in measuring the position when we have measured the uncertainty in its velocity is not very significant. But what happens in the case of an electron? If you now replace this for an electron, what will be the difference? Well, the only difference is the mass here will be the mass of the electron, and in such a case, look at the uncertainty. It is 0.0019 meter. So there is an uncertainty of 0.0019 meter. Now remember, considering the size of the electron, this is a humongous number. So there is a very large measure of uncertainty in locating the position of the electron when the uncertainty in its momentum is given to us. I hope that particular point is illustrated by this problem. Now let's use this concept in developing an atom model. What is an electron orbital? These concepts are actually used in developing the concept of an electron orbital. So we are going to improve the Bohr model. In the Bohr model, an orbit n equal to 1, n equal to 2 are all clearly defined. But that model cannot be applied to higher elements. So let's see how quantum mechanical model can be applied there. According to quantum mechanical model, the location of an electron is specified by an orbital, contrary to what an orbit did in the Bohr model. An orbital indicates the probable location of the electron. You see, quantum mechanics only gives you the probability that an electron can be found in a certain location. It doesn't tell you exactly where it is. So an orbital indicates a probable location of the electron in an atom instead of a definite path they follow. So that clear orbit in the case of a Bohr model is now looking a little fuzzy. It is not very clear because you don't have a clear path of the electron. We don't know exactly where the electron can be found. So this gives rise to the idea of an electron cloud around the nucleus. That means there are regions where the probability of finding the electron is greater than other regions. But the probability value of finding the electron around the nucleus varies at different places, giving rise to the idea of an electron cloud. Now here, not a very good picture though, but it gives you an idea of what an electron cloud looks like. Now, the cloud density reflects the probability that the electron is in a particular region. If the cloud density is large, it means the probability for finding the electron there is greater. If the cloud density is not very high, the probability of finding the electron there is very low. The probable location of the electron in an orbital is described by a series of numbers called quantum numbers. Now, you are familiar with one quantum number we used in Bohr model. What was that quantum number called? We call it the principal quantum number. N equal to 1, the first orbit. N equal to 2, the second orbit or the energy level, and so on. Now, we're going to expand that in the quantum mechanical model. In the quantum mechanical model, you don't have an electron sitting exactly at n equal to 1. But we will use that quantum number again here. But we will add more quantum numbers. Well, that makes it a little more complicated. We have a set of 4 quantum numbers in here. The quantum model of the atom uses 4 quantum numbers to describe the arrangements of electron in an atom. So in addition to the principal quantum number, we will use 3 more additional quantum numbers to describe exactly where the electron is. Now, the first is the principal quantum number, n equal to 1, 2, 3, and so on. The second is the orbital quantum number, and we represent it by L. And L can have n minus 1 values. That means for each n, there can be different L values. So if n equal to 3, what are the possible L values? L can be 0, 1, or 2. There are n minus 1 values. For n equal to 3, L can be 2, 1, or 0. There are 3 possible values of L for one n value there, n equal to 3. Now the third is the magnetic quantum number. We write it as m sub L. And that can have values. M sub L is plus or minus L. So, how many ml values can there be for n equal to 3? Can you tell me? ml is plus or minus L. That means for n equal to 3, ml can have 2, 1, 0, then minus 1, minus 2, or minus 1, minus 2, minus 1, 0, 1, and 2. There are 5 different values of ml for n equal to 3. And the fourth quantum number is called the magnetic spin quantum number. And they have just 2 values. It can be positive 1/2 or a negative 1/2. So, we have now all these quantum numbers, and we're going to use all these quantum numbers to locate exactly where an electron is in the atom. In other words, these quantum numbers actually gives you an address to locate the position of the atom. And now this is where quantum mechanical model is actually more precise than any other model we discussed so far. Now, it is common to refer the energy level corresponding to a given n value as a shell. So, n equal to 1 will be the first electron shell, n equal to 2 will be the second shell, and so on. And then there will be subshells corresponding to L values. So there are shells and then subshells, and we will have a look at that. I have made a very primitive diagram here. If you look at n equal to 1, well, n equal to 1 don't have any more subshell, because n equal to 1, L can have only one value, that is 0. Is that right? So for the n equal to 1 shell, there is only one subshell, which is itself. But n equal to 2, L can have 0 and 1. Is that right? 0 and 1, n equal to 2. That means there are 2 subshells there. So the n equal to 2 becomes a little more complex. N equal to 3 becomes a lot more complex. So you have now, in place of board model having clear orbits, here we have shells, and each shell has subshells. Well, subshells are named S, P, D, F, G, and so on. Now, the subshell S stands for the value of L equal to 0. The subshell P stands for the value L equal to 1, and so on. So, subshell G stands for L equal to 0, 1, 2, 3, 4. So, for each L value, we name the subshell. Now, to specify an electron, we use n as a number and followed by the letter that stands for L. In other words, when you specify an electron, you got to say which shell and which subshell. Okay. Now, for example, 1s corresponds to an electron in the shell 1 in the S subshell. Now 2p, you see, you can see that is the address of the electron. 2p is an electron that is in the shell n equal to 2 and its subshell corresponding to L equal to 1. Now, how about the 3d? 3d corresponds to the third shell, n equal to 3, and its subshell corresponds to L equal to 2. L equal to 2. Or n equal to, yes, so n equal to 3 and L equal to 2 is a 3D address. Now, what does 1s2 means? When you have a number put as a superscript, that number is the number of electrons in that shell. So 1s2 means in the shell, in the first shell, in the S subshell, there are 2 electrons. You can see that address is now specified. What does 2p6 means? In the second shell, in the P subshell corresponds to L equal to 1, there are 6 electrons. 2p6. Now, so it means that n equal to 2, there are 6 electrons in the P subshell. Now, this arrangement is known as the electron configuration. I'm sure most of you have done a chemistry course and you are familiar with the concept of electron configuration. Now, the placement of the electrons in a particular configuration is based on 2 principles, very important principles. The first principle is called the Aufbau principle, states that an electron will occupy the lowest possible energy available. Now, unlike in a class where students would come and sit as far away from the professor, is that right? You all do that. In an atom, that's not allowed. Electrons will occupy the lowest energy level, which are closer to the nucleus first, and then systematically fill the levels that are outside. That is the first principle. The second principle is called the Pauli's exclusion principle. That's a very important principle. What does it tell you? It tells you that no 2 electrons can have the same set of quantum numbers. Well, what does that mean? No 2 electrons can have the same set of quantum numbers. For example, let's consider the first subshell, n equal to 1, S subshell. N equal to 1, then L equal to 0. If L equal to 0, ML also equal to 0 because ML is plus or minus L. And MS can have either positive or negative value. So, in that S subshell, 1 electron can have this set of quantum numbers. N equal to 1, L equal to 0, ML equal to 0, and MS equal to 1/2. Now, the Pauli's exclusion principle says no other electron in the atom can have all these values the same. That means if there is a second electron in that shell, then its quantum numbers will be n equal to 1, L equal to 0, ML equal to 0, MS equal to -1/2. So you can have two electrons having different sets. You can see all these values are the same, but these are different. And you cannot have all these four values the same for any two electrons. That is what Pauli's exclusion principle says. No two electrons can have the same set of quantum numbers. Now, the energy level n equal to 1 can have only two electrons because of that particular principle, which correspond to n equal to 1, L equal to 0, ML equal to 0, and MS equal to either 1/2 or -1/2. Now, if you go to n equal to 2, the level n equal to 2, how many electrons can be there at n equal to 2? Can you locate that? Can you tell me how many electrons can there be at n equal to 2? Now look at this. N equal to 2 can have two L values, L equal to 0, L equal to 1. L equal to 0 is the S subshell. And S subshell can have L equal to 0, N equal to 2, L equal to 0, ML equal to 0, MS equal to plus or minus 1/2. That means there are two electrons in here. Alright? I'm writing it invisibly. In the S subshell for N equal to 2, there can be two electrons. If you now come to L equal to 1, L equal to 1 will correspond to ML. ML can have plus or minus 1 or 0. And you can see this will give you three combinations. And each of these three combinations can have MS either plus or minus. That means there are 6 electrons corresponding to L equal to 1 on the P subshell. So the S subshell can have 2 electrons and the P subshell can have 6 electrons, and therefore N equal to 2 can have how many electrons? 8 electrons. Alright, now I want you to figure out how many electrons can there be in the shell N equal to 3. You can see that's very simple now. So, you are now able to decide on the number of electrons per shell and in each subshell. In an S subshell there can only be 2 electrons. In a P subshell there can only be 6 electrons, and so on. Now, similarly, the level n equal to 2 can have 8 electrons, n equal to 318, and so on. Now, aluminum with 13 electrons has the configuration. Look at this. First, the electrons will have to fill the first shell, n equal to 1. And n equal to 1 has only one subshell, that is S. And that subshell can have 2 electrons. So 1s2 means 2 electrons in the first shell. And then you go to n equal to 2. That has S and P subshells. S subshell can have 2 electrons. P subshell can have 6 electrons. And once those S and P are filled, then you go to the third shell, n equal to 3. The S subshell there can have 2 electrons, and the remaining 1 electron will be in the P subshell. The total number of electrons will be now 2 plus 2, 4 plus 6, 10, 12, 13 electrons. So this is the electron configuration of aluminum. Nickel with 28 electrons has this configuration. You can actually now figure out the configuration of many more elements. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8, and so on. Well, here again is a description of the various energy shells, and of course each shell has its own subshells. Now, here is a picture of an orbital. What is an orbital? An orbital gives you the probability of finding an electron in a given space. So if you look at the S subshell, it will look like this. The density of the shading gives you the probability of finding an electron. If the density is greater, the probability is greater, and so on. The P subshell is like a dumbbell. The D subshell is a double dumbbell, and so on. Of course, the shaded area represents the probability of finding an electron in that shell. Alright, we talked about all this. Now, you remember I drew the energy level diagram in the case of the Bohr model, and I gave you the energy values for each, n equal to 1, n equal to 2, and so on. But if you now come and draw the energy level diagram for the quantum model, those levels are more complex because each level has subshells. So, if you now draw the energy levels, you can see n equal to 1 has just one subshell, 1s. If you now go to n equal to 2, look at this, n equal to 2 has 2s and 2p. N equal to 3 has 3s, 3p, and 3d. N equal to 4 can have 4s, 4p, 4d, 4f. And you can see they also overlap. Now, that's not going to be our concern in this lesson. That will be dealt with in a chemistry lesson. But what we are interested in is, because of these various subshells for each shell, the electron transitions can now have a lot more complex transitions. Now, you remember the picture I started with this lesson, the complex spectrum of helium? There are a lot more lines in there. Why? Because there are a lot more energy levels between which the transitions can take place. It is no longer a simple picture of the Bohr model. There are a lot more possibilities or combinations of possibilities for electron transfer. That's right. There are many more intermediate levels of energy, and there are thousands of possibilities of electronic transitions between these levels, and therefore you can have thousands more radiations than in the simple case of a hydrogen. Whereas Bohr model could only explain hydrogen atom with just one electron, the quantum model explains all observed phenomena for all elements. So we have actually found a good model of the atom. The quantum mechanical model clearly explains a lot of observed phenomena. So I would like you to appreciate the story of the atom models that we developed. It's been a great story that started many centuries ago and is still going on. The story is not finished yet because we still don't know what the building block of the universe is. If you know exactly what atoms are made of, then we should know what the building blocks are. If you know what the building blocks are, then we know a much more clear picture of what we are and where we come from. Do we know anything of that sort? I don't think we know. I don't think we have a clear picture. Well, the foundations of this theory is now shifting. The frontiers of physics is now on what is called the string theory. So, the fundamental model that we have been talking about so far, we have been talking about a standard model of particle physics. Now, what does the standard model of particle physics involve? Now, the standard model describes the fundamental building blocks and the forces through which they interact. Now, so far, our understanding of the universe is based on the standard model of the atom, the standard model of the particle physics. Now, that gives us a not very clear, but rather clear picture of the fundamental building blocks and the forces that hold them together. Now, according to this theory, there are 12 basic building blocks. And these 12 are 6 quarks. There is an up quark, a down quark, a charmed quark, a strange quark, a bottom quark, and a top quark. So there are 6 quarks, and there are 6 other particles called leptons. So according to the Standard Model, the building blocks of all matter are actually the 6 quarks and 6 leptons. Well, the scope of this lesson does not allow me to go any further than that, because these are very complex ideas. Now, there are 4 fundamental forces, which are gravity, electromagnetism, weak and strong nuclear forces. In fact, the whole universe is held together the way we understand it now due to these 4 forces, these fundamental forces. Force of gravity, which keeps all the planets, the stars, the galaxies, and everything in its place. And you can see the whole universe is actually in a perpetual motion. And all these are made possible by the force of gravity. Electromagnetism is a force that is responsible for holding all the particles together to form the materials that we know around us. And what are the forces that hold the atoms together? We talked about an atom as a nucleus consisting of protons and neutrons. Protons are positively charged. How can you hold a bunch of positively charged particles in a bag? Will they be stable? Well, in fact, they should all be repelling, is that right? And destroy the whole world. If that repelling comes into effect, no atoms can be stable, and the universe there cannot be stable, and nothing can exist. But these strong forces are the forces that hold the nuclear particles together. Now, if you bring 2 particles that hate each other, that repel each other, and you keep them at a very small distance, that hating force, the repelling force, will turn into an attractive force. And that is the strong force. So it is a strong force that holds the nuclear particles together. Then there are weak forces. Weak forces are forces that help nuclear particles to turn from one particle to the other. There are always those conversions that is taking place. So all these forces put together is responsible for the universe as we know of now. Do you know how the gravity compares with electromagnetism? How strong are these forces? For example, if you consider 2 electrons, or an electron and a proton, the electrostatic force between them is K E squared over R squared. And the gravitational force between them is G M1 M2 over R squared. Now, if you use the known values of these and calculate these forces, you will see that the electromagnetic force is 10 to the power of 39 times as great as the gravitational force. So compared to electromagnetic force, the gravitational force is very, very weak. So you must have a fair idea of how these forces stand. At the same time, these strong forces are very strong. The Standard Model describes the behavior of all these particles and the forces except gravity. You see, if we believe that the universe originated as a result of the Big Bang, have you heard of that theory? That the whole, everything in the universe, very many billions and billions of years ago, was concentrated at a very small point, say 10 to the power of negative 35 meter. Can you think of such a point? And the Big Bang originated from there, and ever since that time, the universe has been expanding. Now, if everything originated from there at that point, and that everything that we have is controlled by these four forces, then it is reasonable to assume that these four forces must have a single origin. In other words, we must be able to unify these four forces at some level. Now, what has happened is, the theory we know, the Standard Model, has unified electromagnetism, weak and strong forces. But the theory cannot find a common link between these three forces and gravity. Now, quantum mechanics clearly gives you a way of finding a link between these three, but it has not given us a way to unify all these forces. Now, one of the reasons why Einstein was very wary of quantum mechanics, Einstein did not accept quantum mechanics as it is until his death, because of this particular problem. And also, he didn't believe that an electron cannot be detected precisely. Now, he couldn't buy the idea that an electron exists only as a probability value. He said God doesn't play with dice. If God created the universe, he must assign precise measurements to all these quantities. Well, we cannot spend a lot of time on this, so we need to move on. In the last few decades, string theory has emerged as the most promising candidate for a microscopic theory of everything. Theory of everything. That is, it encompasses all these four forces and all the fundamental particles. We can unify everything together under the string theory premise. Now, there are many scientists, physicists, who don't believe in string theory, whereas some others who are great proponents of it. It is based on beautiful mathematics, and it explains a lot of these phenomena very clearly. Now, it attempts to unify all existing theories about the universe. And so, it must be a formidable theory. And I urge you to spend some time finding some material about string theory and try to learn a bit about it, how it brings about this unifying effort to unify all these existing forces into a single origin. According to string theory, everything in the universe, all particles and all forces, remember we talked about the 12 fundamental particles and 4 fundamental forces. According to string theory, all these particles and forces are made up of basic strings vibrating like this. Now, these strings can vibrate in many different modes. You can see now it's not really vibrating. Now look at the mode of vibration there. This represents a different energy of vibration. So this is the same basic string that can vibrate in many different modes. You can see that's the mode number 2. And I increased the frequency. That's mode number 3. Here you are. Not getting it right. Is that right? Okay. And the string can vibrate in many different modes. So, all these particles, depending on the mode of vibration, you have a different particle and a different force. Now, I want you to see this here. So this now represents, well, the string had gone off the vibrator. Let me see if I can produce another mode of vibration there. There I have the 4th mode. Now, each of these different modes represent a different particles. So everything that we see in the universe, all particles and all forces, are actually made up of these tiny vibrating strings, and depending on the mode of vibration, these strings can represent different particles. If one mode of vibration is an electron, another mode will be a proton, and so on. Not as simple as what I'm saying, but basically that's what the idea is. Here is another illustration of the vibrations of the fundamental string. It can vibrate in very many different modes. And a string can be a closed string like this or an open string. It can be many forms of the fundamental string. So a particle is like a note played on a guitar. You know that when we talked about the vibrations of strings, we used the same principle. When you pluck a string, it vibrates producing a note. So one mode of vibration is a particular note, particular frequency. Another mode is a higher frequency or a lower frequency. In the same way, one mode of vibration of a string is one particle of one mass of certain energy. Another mode of vibration is another particle. So this is an ever-changing different modes of vibrations of particle. The only difference between one string and another, whether it is a heavy particle that is part of an atom or a massless particle that carries light, that its resonant patterns are different. What I showed you in the demonstration are the different resonant patterns of the string. So depending on the different resonant patterns, the string can represent either a heavy particle that is part of the atom or a particle that is massless, like a neutrino, or a light particle, photon, can be represented by a vibrating string. Now the vibrational pattern determines what kind of a particle the string represents. One resonant pattern makes it a photon, another makes it a heavy particle within the nucleus of the atom. So a string theory is actually a simplified theory that everything in the universe is made up of these fundamental one-dimensional strings. But it is not as simple as we explained. It is based on very complex mathematics. Now, what is the consequence of the string theory, the consequence of this mathematics? While the strings in the theory are one-dimensional, the mathematics describing the string requires 11 dimensions for the universe. Well, yes, there's some theory which goes all the way to 28 dimensions. Now, how do we explain these 11 dimensions? We are familiar with 4 dimensions. These 3, X, Y, Z, the spatial dimensions, and the other time dimensions. Can you think of 5 dimensions, or 6 dimensions, 11 dimensions? Well, that takes us out of the periphery of our known universe. Now, if you want to appreciate it, think of a one-dimensional person. A person or an animal or a creature that comes from a one-dimensional universe. Can you think of such a person? Well, suppose I am such a person and I am looking for my friend in a three-dimensional world. I say, I'm looking for Robert. And now Tony tells me, Robert is on your right side. Now, I'm a one-dimensional person. I don't understand the difference between left and right, up and... Do I? No, I only understand the difference between front and back, one dimension. I have no concept of left and right. So, if Tony tells me Robert can be found on my right, I will move back and forth. I will not find Robert because I'm not a three-dimensional person. In the same way, think of somebody coming from a seven-dimensional universe. For a seven-dimensional universe, our universe is four-dimensional. That means that person coming from a seven-dimensional universe actually can walk through the walls In other words, that person can materialize right in front of you. Well, does it tell you some stories? It leaves a lot of room open for you to speculate about the nature of the universe. The universe is not really a simple model as we think. I believe that the universe as we know it is only one of the many millions and billions of other universes. There are other universes of different dimensions. We, poor people, are 4 dimensions. All other dimensions are hidden from us. We are trapped in the 3 spatial and 1 time dimensions. That means we can probably get out of this trap. Maybe when we die. What do you think? We probably will go to a universe, we will have access to a universe that are of higher dimensions. Well, I don't know if anybody has experienced sometime, I thought my grandmother was sitting next to me, but my grandmother died 15 years ago. Well, that grandmother may be in a 7-dimensional universe. She's got access to you, but you have no access to her. Well, this is simply my thought. Well, why I have done this is to give you some idea about thinking about the universe. You see, these are complex ideas, and trying to find an answer for what is this universe made of, what is the basic building structure, takes us all the way out into the wilderness, and we wander in this multi-dimensional universe, which are probably linked by these wormholes. Have you heard of those things? That you can move from one universe to the other through these wormholes. Now, do some readings on it, and let me know if you find out something new about this. So if string theory is to be a theory of quantum gravity, then the average size of a string should be somewhere near the length scale of quantum gravity, called the Planck length. The Planck length is 10 to the negative 35 meters. So, if this string theory is, or quantum gravity, according to the quantum gravity theory, these strings that describes the fundamental building blocks of all matter cannot be greater than this 10 to the power of negative 35. Now, how big is it? Is it possible for us to detect that by any means? Well, so it's going to remain elusive to us. We are never going to detect a string like that. That means this theory is going to remain a theory. We will never be able to experimentally prove it. Now, this is one of the great objections about string theory. String theory is very abstract. It only exists as a theory. It cannot be experienced. So unfortunately, this means that strings are way too small to see by current expected particle physics technology, and so it remains elusive to us. Now, we still don't know what the fundamental theory behind the string theory is, but judging from the established relationships, it must be a very interesting and rich theory, one where the distance scale, the coupling strengths, and even the number of dimensions in space-time are not fixed concepts, but fluid entities that shift from one point of view to another. In other words, from the theoretician's point of view, these can keep changing. So how close are we to describing what our universe is? Our universe is a very complex thing. And what we have achieved in these 3 segments of lessons is to trace through the story of how all these things evolved. Has it given us any conclusive proof of what the building block of our universe is? No. So the frontiers are still shifting. Physics is an ever-evolving subject. It never gives you any satisfactory answer which you can say, oh, I have found out. Eureka! Moment never comes. It's always that leads you on to the next step. I hope you will pick an interest on it and do some reading and get back to me and tell me what you have learned about it.